Welcome to the lecture 29, and this is the last lecture. I was supposed to do 30 lectures, but then I understood because it's an online course, I could finish with even one less. Idea was not that. Basically, in online teaching, your level of space is very high. There is no question answer session going on at the same time. So we always tend to teach more in every lecture than what is expected to be taught in an offline course. So hence, this is the last lecture, and I only can hope you have enjoyed the course, you have enjoyed the content of the course. I am very open for discussions or questions or anything which you have failed. I may have made mistakes, or I may have not covered, or I have given some reasons which are not maybe proper according to you. So please do use this forum to tell me, provide me the feedback so that I can improve in my future courses on this NPTEL forum. So in this lecture, we are going to talk about polymer nanocomposites that we discussed about it, right? So we have discussed over these 28 lectures various aspects of nanomaterials. We learned the effect of size on the various properties, and we have also tried to understand the structure, nanostructure, issues of the nanostructure, how they are correlated with the properties of the nanomaterials. So other than size, many other aspects of size comes into picture, right? Like arrangements at the nanoscale, and also how you put things together. So that's one of the important contentious issues in nanocomposites. So the last lecture we did some discussions about the carbon-based nanomaterials. In the following, I am going to just give small recap, and then I will talk about some of the important aspects of polymer nanocomposites, because this is something which is coming up very sharply, and probably these composites will find use in the real time in times to come. So what we discussed about the carbon nanomaterials, we talked about how the carbon can self-assemble to produce different kind of nanostructures. We started with C60 buckyballs, and we showed that by putting arrangements of hexagon and pentagons of the carbon atoms, basically we can generate this kind of buckyballs. And we also understood, or rather we also tried to show you that the carbon nanotubes can be produced using a single layer graphene by simply wrapping around a cylinder. And graphene is the recent nanostructure carbon materials. Although I didn't talk about nanodiamonds, they are also very useful materials in the carbon family. Since nanodiamonds are used in other purposes like coatings, high hardness can be easily obtained using nanodiamonds, and diamonds can also act as lubricants in various applications. So therefore, the varieties of nanostructures can be produced using carbon-based nanomaterials. But the basic thing is this graphite. Graphitic network is the underlying structure for almost all the nanostructures except for a diamond. So you know that graphite is basically a layer structure. It has a hexagonal network in each layer, and within the layer you have van der Waals bonds between the sheets of carbon atoms. So we can always devise ways and means to cut off these van der Waals bonds and produce single layer of the hexagonal network, which is very easy to say but not easy to do in real experiments, and that's why it took so much time. Even though graphite was discovered 1500 BC, so AD, sorry. So but the discovery of these nanostructures was very late, maybe 20 to 30 years, not more than that. So that's the difference of the time scale when you want to produce a new material. So, you can use this sheet of graphene to produce different kind of nanostructures, like you can wrap around a ball and create zero-dimensional nanostructure like buckyball, which came in 1986, and you can also wrap around a cylinder, produce nanotubes. If you wrap several cylinders, you can put multiple nanotubes, or you can even cut off each of the sheets, so you can produce 2D graphene or 2D materials like graphene. Okay. So, these different kind of nanostructures can be easily produced from one single thing, that is called graphite. When you stack them together, you produce this graphite. So, that is the connecting link for all these beasts. Okay. I call it beasts because they are very powerful materials. They can be widely used in different kinds of applications. That is why I call them as a beast. So, that means what? The basic underlying structure, although we know is basically a single layer of graphene, but it took a lot of time to understand that aspect. Now is the question of how we can apply it and all those things. So, this can be produced mostly by arc discharge method, and in case of arc discharge of graphite, graphites tend to melt, and during melting most of the graphite will solidify as a glassy particles, but some of them will undercool heavily and then produce this kind of nano structure materials like nanorods or nanotubes actually. Or you can use even catalyst in a technique which is very popular. You can put this graphitic material in a tabular furnace, and you can always apply catalysts like iron or nickel, and then you can start producing graphene at a much lower temperature. Sorry, nanotube is not much lower temperature. That is something about 1100 degrees Celsius temperature can be used to produce this kind of nanotubes. Okay. So, here in this case actually a gaseous mixture of methane and nitrogen or carbon or the argon is used and passed through this catalyst, then you can produce nanotubes, and the temperature is much lower. It is almost 1100 degrees Celsius temperature can be used. Well, this is one such picture. You can see this nickel catalyst is used to produce these nanotubes, and nickel is visible at the end of the nanotube, and this micrograph clearly confirms that this catalyst can be easily used to produce this kind of Cnts. Well, graphene can be produced in different routes. One of the ways basically mechanical exfoliations. In mechanical exfoliations, you can take a graphite and put it within the double-sided tap, and then you can open this, peel off the tap. So, once you peel off the tap, the thin layer of graphite can come off, and it can produce graphene. This is how the graphene was discovered, and you can see these thin layers under optical microscope, and then you will find the layers which are dead thin, they will be having almost 99% transmission of light. That is how the Grimm and Novoselov discovered graphene and awarded Nobel Prize for this. You can also use chemical exfoliations, oxidative exfoliations, electrochemical exfoliations, or liquid phase exfoliations. There are 3 different techniques possible. Oxidative exfoliation basically use oxidation of graphite, and it can exfoliate and produce different layers of the graphite oxides, and then you can reduce this graphite oxide to graphene oxide, or reduce what you call a reduced graphene oxide or RGO. You can always produce using electrochemical exfoliations simply by discharging between the 2 electrodes. You can also produce graphene by liquid phase exfoliation also. So, there are many ways you can do that. And third technique is producing with CVD or chemical vapor depositions. We discussed about it. You can use methane gas passed on the nickel catalyst or nickel plate, which is kept at 1100 to 1200 Celsius temperature, and this methane will decompose into carbon and gaseous hydrogen, or basically moisture. It can react with atmospheric moisture and produce moisture, and oxygen produce atmospheric moisture. It can produce such a kind of carbon can dissolve into nickel at the temperature. When the supersaturation will be reached for the nickel, then this carbon will come out and form like a graphene. So, this is how it is used. You can use this CNT and nanotubes, CNTs and graphene for various purposes like field effect transistors or hydrogen storage or supercapacitor. Okay, this is supercapacitor, this is hydrogen storage. Graphene can be used for energy storage, transistor, or even waveguides. This is what we have seen in the last lecture. And there are many other 2D materials. Most important are the MOS2 and WS2, and they are also produced in a similar way. You can see this is the WS2 multi-wall nanotubes, or on the right side you can see here the multi-wall fluorine obtained from the MOS2. Okay, so you can do that. You can always produce thin sheets of MOS2 using by sonochemical route, which we have discussed in earlier part of this course. So as you can see, there are various 2D materials can be easily produced during this purpose. So now let us come back to our discussion today. This is polymer nanocomposites. Okay, what are nanocomposites? We have already discussed about it. They are actually a class of materials in which one or more phases are in nanoscale dimensions. It can be 0D, 1D, or 2D, and this nanomaterial is embedded in a matrix called metallic, ceramics, or polymer. General idea is that addition of the nanoscale second phase will create synergy between the various constitutions and novel properties can be achieved. The properties of nanocomposites rely on a range of variables, particularly the matrix materials, which can exhibit nanoscale dimensions, loading, even degree of dispersion, size, shape obviously, and in addition orientations of this second phase. So among the various nanocomposites types, the polymer-matrix composites have been the widely studied one, because you can have different kinds of variations possible in polymer-matrix composites. So much like any traditional composite system, polymer-matrix nanocomposite consists of a matrix which is made of a polymer material, and the second phase can be anything like nanotubes also, graphene also, or even ceramics, metallic particles can be put up. So this second phase matrix is what is which is in nanoscale dimensions. So that is what is shown in the picture. You can see this is a polymer matrix, and then you have put this particle inside the matrix which is nanoscale. So they are in spherical shapes. So we will talk about the left side picture a little later. As you know, polymers undergo glass transitions. Most of the polymers actually are amorphous or semi-amorphous type. So this amorphous phase will undergo glass transition, and then if you keep on heating further, it will become rubbery at high temperature. So that's why the application of these composites are limited to temperature below Tg, or the glass transition temperature. And this is very common plot for the glassy materials which are widely used. As in, if every glassy material, amorphous material, you have a glass transition temperature. About the glass transition temperature, material will become rubbery and liquid like. So therefore, it cannot be used at the temperature. So major limitations of the polymer nanocomposites is the temperature issue. You cannot use it at high temperature compared to the ceramic and the metallic nanocomposites. That is one of the major limitations. Okay. So in addition to that, due to these nanoparticles present at the D1 page, the interface to volume ratio is significantly higher than in conventional composites. As a result, volume fraction of the second page can be reduced without degradation of the desired properties. Polymer-matrix composite systems can be obviously different types: thermoplastic, thermoset, or elastomer. So let me talk about a little bit about that. But before that, let me tell you this is also nanocomposites. This is basically aluminum copper alloy. You can see needle shaped nanoscale precipitates in aluminum matrix, and these particles are actually growing in various orientations, and this is routinely used in the real material synthesis. Aluminum 4% copper alloy, which is called duralumin, is used as a material for the aerospace industries, and this is the microstructure. And this was discovered long back, before even the concept of nanostructured material came up into actual use or actual practice. So hence this picture is taken from the book of Michael Ashby and others. Let me acknowledge them for this purpose. Other than that, this picture can be available in various published paper from late 50s to 1970s. You can find such a kind of microstructures nicely prepared from edge-hardenable aluminum copper alloys. So that is basically the idea of nanocomposites, as you can see. So hence the basic idea is the compounds. What are polymers? Compound consisting of long chain molecules made up of repeating units are basically called polymers, right? So we will have a small discussions about polymer, then we will go for the composites and discuss, because some of you may have forgotten about polymers. Let us have a recap of that. The polymers are basically low density, high normal strength, and they have reasonably good thermal and electrical conductivity. Strength to weight ratio is comparable with many alloy steels because they have a very low density, and they are very prone to instability because of substantial clip and cold flow at all temperature. Rigidity and fatigue strength much lower than the metals, and they are normally used below 350 degrees Celsius temperature, not more than that. Most importantly, polymers forms living organisms and they are vital processes of life. I always compare polymer like a bowl of spaghetti. We all know spaghetti. You can always see this is the network of different polymeric chains in a real material. Well, polymers, as I said, they can be classified into three different types: thermoplastics, thermoset, and elastomers. Thermoplastic and thermoset are the ones which consist of plastics, which you see in the real life, and elastomers are basically rubbery material, right? So thermoplastics basically can be molded, thermosets cannot be. They have, once they are produced, you can't remelt and reuse, but thermoplastic can be used again and again. That is why they are called thermoplastics. So as you heat the temperature, they will melt, and again they can then form the plastics. But thermosets are like the ones like bakelite, which once you set, you cannot get it back. So this is basically the problem of polymeric material. Most of the polymeric materials, hence thermoplastic materials are basically more widely used in thermosets. Elastomers, you all know from the literature, elastomers are basically rubber bands, and even tires are also elastomers. They are widely used in the materials in the community. Well, so as you said that thermoplastics are basically solid at room temperature, viscous liquid at high temperature, which allows them to be shaped into products. Heating and cooling cycle can be repeated without degradations. Examples are basically nylons, acrylics, cellulose, or PVC. They constitute almost 70% of the polymer produced. As I said, they are the widely used ones, and they can be molded, extruded, rolled. On the other hand, thermosets are softened when they heated, but hardened when they cooled into an infusible solid. You cannot melt it back again. They get cured, and this curing is basically reversible. Reheating can burn and charge the material. Example, epoxy, phenolics, and even certain polyesters. They are used as the knobs and handles of the pots and pans and the light switches. Rubbers that undergo large elastic deformations when subject to forces or stresses. They can retain original shape and size of the stress material removal. Naturally available synthetic can be produced, rubbers are both, and they can be additive bended to produce specific mechanical properties. They are widely used in various applications like corrosion, abrasion protections, vibrational shock absorption, electrical insulations, and non-skid surfaces. There are different products like tires, foot gears, gaskets. Most of the gaskets, seals, and floorings are used. Okay. So what are the fundamental things about the polymers? As I said, polymers are synthesized by joining many small molecules together into a very large molecule called macromolecules, right? So obviously the major process which is used to produce polymers is polymerizations, right? There can be two types of polymerization: addition and step polymerization. What is addition polymerization? Well, addition polymerization is basically very simple. Here I am showing you the case of polyethylene. You can take one molecule of ethylene and join the molecules as large many numbers as possible. They are called polyethylene. And nylon is produced by step polymerization because it has different groups, like this is amyl groups or urea groups or ethyl groups. So therefore they will be produced by other step kind of polymerization techniques. Okay. Now addition polymerization is like this. You can have monomers, then monomers will join from dimers, dimers will then join and form polymers. Okay. So you can do that. Step polymerization is like that. Once you have N mer, you can add a monomer, then you can produce N plus 1 mer. N1 mer can be then added to N2 mer, and then you can join these two. It's called step polymerizations. Okay, that means different types of monomers can be joined and produce a polymer. That is what happens in step polymerization, as you can clearly see that. So fundamentally, the different polymers can be produced by both these techniques, the additive polymerization or the step polymerizations, and this is very commonly available routinely. So, chains in the polymers can be different types based on how you produce. There can be either simple linear chains as you see here, or they can be also branch like this or this or this or this. They can be also cross links, right? You can clearly see they can be other cross links, right? They can be also tidally cross links, very, very tidally cross links. Okay, you can clearly see that how the cross linking is very, all the directions, and that's why the three-dimensional poly structures can be built up. Once you have tidally cross link structure, you can build the three-dimensional polymers. So, this is what normally routinely we find for the most of the polymeric products, that they are linked in a different manners. Okay. Now, you can also have copolymers or homopolymers. Okay. This is homo. Homo means similar type. Sorry, there's a mistake here. Okay. So, homopolymers means you can have one type like ethylene groups, or you can see C2H3Cl groups. Copolymer means there are two types of. One is called ethyl groups, other is called methyl poly. Okay. So, you can have different types of groups, and they can have different values of N and M. Then you can also have alternating things for the copolymers, you can see that, or you have a random, you can have a block copolymer, or you can have a grafted copolymer. You can do grafting also, like hair grafting in your head. So, all kinds of situations are possible to produce different kinds of the polymeric substances. Okay. Now, polymers, as I said, they are mostly amorphous, but they are not fully amorphous. There will be always some crystallinity presence in this. Okay. And these crystalline structures are basically randomly present in the material. As you can see here, I am showing this. There is a crystalline structure, there is a amorphous structure, or you can have such a kind of folded regions also possible. So, what is the meaning of this? You can have a bit of crystallinity in the polymers, and this actually affects the properties of the polymers extensively. When you add these nanomaterials like metallic ceramics or carbon based into the polymers, these kind of things can happen actually. The amorphous polymer can get crystallized into some part of it as a crystalline polymers. This is what something is very nice picture taken from Mass Ashby's book. You can clearly see these are the regions of crystalline or order regions, which are called crystalline regions. Okay, and this is the region of the random oriented. When you have completely total disorder, this is what is called amorphous polymer, completely amorphous. You can see they are random completely. So, this is how actually different kinds of polymers can present, and you can have in the nanocomposites, you can have either of these phases can be either crystalline, or these phases can be otherwise amorphous also. You can always put carbon black into the an amorphous polymer, produce polymer nanocomposites. That is also possible. Well, how polymer nanocomposites are produced? Some of these things I am showing you, they are done research in my lab by my students. Okay, so I will be using those pictures also. As you see, this is a polymer nanocomposite preparation using Cnts. First, you do that, you put the Cnts into acetone and then sonicate it for long. And you do it because both the Cnt and the epoxy solutions to that they get there is not much agglomeration happens in the actual picture. Then you can stir at very high RPM for 60 degrees Celsius about 1 hour. This is the second step you can see here. This will be followed by pouring of this Cnt acetone mixture in the epoxy. Okay, and once you do that, then you can again stir it at 65 degree for 1 hour for better mixing, and then you can sonicate it again for large hours, and after that you can do vacuum degassing, so that all the water everything goes off. After that you can mix the hardener of the epoxy. Actually epoxy has a hardener also, and then it will be hardened, and then you can hot press at 60 degrees Celsius temperature by application of some pressure for about 20 to 30 minutes. Then you can get easily nanopillar based laminates. You can one by one you can produce laminates, And after that, you can cut the laminates and you can do different kinds of testing. So basically, the important aspect of this preparation fabrication route is that this is a widely used fabrication route. You know that you have to mix them very well. Once you mix them properly, then you can pour in a container and degas, vacuum degas. That is widely used technique. Okay, vacuum degassing is not a very difficult thing to understand. You can remove by vacuum degassing all the water and other diseases which are easily removable, and you can it will leave behind the solid composites. Okay, so that's something which is very routinely practiced in the real world or material world. Okay, you know these composites can show different kinds of properties. Here you see the polyimide composites with nano silicon dioxide having different kinds of transmittance. 0% polyimide, 10%, so 0% silicon dioxide, 10% to about 30%. So the transmission levels changes by different loading. This is the property which is sometimes required for having different level of transmission to light. It can be only normal light or UV. So that is something can be easily obtained. Nanoscale reinforcing phase in a material, what we discuss here, like silicon dioxide or carbon, can be grouped into three categories. They can be nanoparticles like 0 dimensionals, they can be nanotubes, they can be nano pets, or they can be even nano grain materials. In case of nanoparticles, particle size and distribution are of great importance. Depending on the type of nanoparticles added, the mechanical, electrical, electronics, optical properties, or thermal properties will change. In the field of mechanical properties, change in the modulus and strength depends on strongly on the degree of the interaction between the particle and the polymer. In polyvinyl methacrylate or PMMA, like polymer nanocomposites reinforced with alumina, modulus decreases due to weak interaction between the alumina and the PMMA. Whereas if you use polystyrene nanocomposites reinforced with silica, then modulus increase due to strong bonding. So bonding between this second phase of the polymer is very vital. Another advantage of using nanoparticle reinforcement is that their size is smaller than the critical crack lengths typically found in the polymers. So as a result, nanoparticle provide the improved toughness, very high toughness and strength. However, agglomeration of nanoparticles is a big problem in all these things. That's why the strong styrene, everything is used. So hence, agglomeration is a big problem. Hence, several investigations have shown that small level of agglomeration can decrease the strength to failure by several tens of percentage. And additional mechanism that occurs for well dispersed nanoparticles which weakly bonded to the matrix is the phenomenon of gravitations. Okay. In other words, nanoparticle can act as a voids actually. They can create voids which initiate the yielding and increase the volume of material going through the deformations. Nanoparticle can also significantly affect, as I discussed already, the TG or the cast iron temperature. Typically this occurs because nanoparticle influence the mobility of the polymer exchange due to bonding between the particles and the polymer, and even the bridging to the polymer. Okay. So hence, in some cases, a depression in the TG is observed, which is not good news. However, in many cases, the TG temperature increases a lot. Electrical and optical properties of polymer matrices can be also improved by addition of nanoparticle with respect to the electrical properties of the matrix, and this can be done by various arrangements of the nanoparticles in the matrix and type of nanoparticle. Low density polyethylene nanocomposites filled with Z-nano nanoparticle shows extensive improvement in properties as I have shown you here. Let me just go back. Yes, this is the one. You can see this is a picture of Z-nano nanoparticles in a low density polyethylene nanocomposites. It can improve electrical properties a lot. So in terms of optical properties, there is a large development, large interest in the transparent nanocomposites. Okay, transparent nanocomposites are very widely used. This is what I discussed just a couple of minutes back, and with enhanced mechanical and electrical properties. To achieve transparency, the scattering must be minimized, which means the nanoparticles should be as small as possible, while the index of refraction should remain as small as possible of the matrix. For example, addition of nanoparticles of silica dioxide to the silicon dioxide to these things can control the transmissions of the nanocomposites. Furthermore, the addition of nanoscale alumina to gelatin has improved total transmission by as much as 100%. Next, let us talk about a little bit of carbon nanotubes. As you know, the one-dimensional nanomaterials, in particular Cnts, can be used as a reinforcements for the nanocomposites. A comprehensive discussions on this cannot be done because of the shortage of the time, but one can read the different books and find out that the use of Cnts in the composites has received wide scale attention due to their extraordinary physical and mechanical properties. However, to take full advantage of the Cnts nanocomposites application, several critical issues must be addressed. First is the uniform dispersion, which is very difficult to achieve. Second is this alignment of Cnts in the composites. This is very challenging to disperse nicely these Cnts in the matrix, particularly as compared to the that procedure I just discussed just now, because Cnts exhibit smooth surfaces and intrinsic van der Waals interactions, which can promote clustering when in a polymer matrix. So, to address this problem, many people have basically modified the Cnt surfaces, by putting some some kind of a layer on the ceiling or functionalize them. So, that can be done, or you can have shear mixing during mixing process, or you can have surface tension assisted processing also. The different kinds of techniques can be used. This is a typical picture of agglomeration carbon nanotubes. This is taken from the work of P.J. Ferreira and et al. From MIT. I am just using this picture from Michael Ashby's book. So, I acknowledge both of them for the use of this picture for the class. Well, now let us see some of the examples of which we can. These are the works done by my students, and this is the polymer nanocomposites epoxy based, basically using multi-wall Cnts. You can clearly see that the Cnts are present here, there, here. A lot of Cnts are present, and this Cnts basically in many cases got agglomerated. It is very difficult to avoid the agglomeration of the Cnts, but Cnts provide many interesting many improved properties of this nanomaterial. This is the where you can see these are actually Cnts. Some of the cases you can see the pull out of the Cnts also. It is possible to observe that, or they are well dispersed many cases. So, this is something which is routinely found. And now, polymers also used for functionalization and stabilization of Cnts, and you can also stabilize the Cnts to produce different kinds of structures. Like here we can see the different kinds of structures. You can clearly see that these are the different radicals actually which can be used for this purpose. So, in order to, in fact, in addition to uniform dispersion of the polymer matrix, a crucial aspect for providing optimum transparent polymer is orientation of the Cnts. Because of the very high aspect ratio, Cnts possess highly anisotropic mechanical properties. To take advantage of their load carrying efficiency along the axial direction, it is essential that Cnts are well aligned within the matrix. Several methods have been used to do that. So, polystyrene nanocomposites are basically filled with Cnts have been produced compared to the pristine sample. Modulus of aligned composites increase almost by 50%. So, that is something which is widely used in many purposes. In addition, aligned Cnts or polystyrene nanocomposites were also shown to exhibit increased yield strength and ultimate UTS also compared to the pristine ones, due to the fact that Cnts exhibits high electrical conductions. Applications of the magnetic field or electric field have also been used to produce Cnt alignments. It is observed that elastic modulus measured in the direction parallel to the magnetic field was far greater than the perpendicular to the magnetic field. So, in fact, this suggests that alignment of Cnts contributes significantly to the increase in the mechanical properties of these polymer nanocomposites. Finally, the interfacial bonding between the Cnts and the polymer is very important. It is believed that efficiency of the load transfer in nanocomposite depends on the interfacial characteristics of the reinforced phase in the matrix. So, in case of polymer matrix nanocomposite reinforced by Cnts, the main mechanism of load transfer is mechanically interlocking between the CNT and the matrix. So that is the main mechanism. Other than that, you have a chemical bonding or nano-bonded interaction between the CNT and the matrix. In addition, it is believed that key factor in forming a strong bond is the polymer matrix, and the CNT lies in polymer morphology, especially the ability to form large diameter helices around these individual CNTs. Strength of the interface is then due to molecular level entanglements of the CNTs at the matrix. In inclusion of CNTs and polymer matrix nanocomposites can also be used to improve thermal conductivity of this nanocomposite. The CNTs create percolation network in the nanocomposites, okay, to conduct the heat and conductivity up to 3.5 times higher than the what is observed in pristine polymers. However, thermal conductivity nanocomposite is still far from lower than the theoretical value, and this is something which is a big concern. The major reason for discrepancy is the large thermal resistance that exists between the polymer matrix and the CNT surface. Because CNT possesses high surface to volume ratio, when CNT is dispersed in a polymer matrix, large interfacial area creates a significant resistance, and this effect has been attributed to the difference in the phonon dispersion or phonon frequency between the CNT and the polymer matrix. Some solutions have been suggested in the literature to decrease this thermal resistance, and it is proposed to covalently bond the CNTs to the polymer to improve the phonon scattering. But it has also been suggested that multiple CNTs, use of multiple CNTs instead of singular CNTs, because polymer or the multiple CNTs can have smaller aspect ratios, therefore less interfacial area. The use of CNTs in nanocomposites has also improved the thermal stability of the polymeric composites. It has been found that CNTs can improve that. Well, there are many other aspects which can be discussed about that. The last one is basically 2D second phase particles nanocomposites in the polymer nanocomposites. There are plate-like layers materials with a thickness of the order of 1 millimeter with an aspect ratio of 25 above can be used. Most common ones are layered silica structures, okay, which is widely used. This is the one you can see, the layered silica structures. Silica can be used that, and once if you use, you can improve several properties of polymer nanocomposites. Okay, so this is a layered silicon structure, and which can be used as one of the reinforcing materials, and it can lead to improve UV resistance, improve strength, gas permeability, greater dimensional stability. Many other properties can be improved. Okay, so among the layered silicas, mica and smetic clay can also be used. Okay, mica is easily available and can be, you have seen probably, they can be used also for this purpose. They are layer structures. Mica consists of large sheets of silicate with strong bond among the layers. On the other hand, basically they can be used for these purposes. Also, on the other hand, contrary, symmetric clays exhibit weak bonds between the layers. Symmetric clays consist of 3-layered sandwich structure composed of 2 outer layers containing silicon and oxygen bonded to the inner aluminum, magnesium, or any other atoms present there, or the hydroxylic groups. Due to the substitution of the divalent magnesium to divalent aluminum, negative charge can be produced, and this can lead to, and this charge has to be compensated by the absorption of the cations like sodium, potassium, calcium, lithium. Layer structures is shown here in the 2D. You can see that the aluminum, iron, manganese is produced to charge create this charge imbalance, and which later on can be used for better bonding between the polymer matrix. So to overcome this problem, sometimes exchange reactions usually carried out variety of organic cations open the clay structure. Well, so polymers nanocomposite can be used. The two types, conventional composites, intercalated nanocomposites, exfoliated nanocomposites. Okay, so nanoscale layer silicates are proven to be provide much better insight into the properties. So there are many such inunities can be used. I am just telling you only few of the inunities which are there. So with this, I will close this class and close this course. Hope you have enjoyed over the last 3 months this course, and you have enjoyed various parts of the course. and there are always deficiency when we develop a course. It is not possible to cover every subject of the course in a very systematic manner because of time constraint, because of the available literature, and this field is basically evolving. This is not a field which is already mature enough. This field is evolving, so the subject matters are also available in many cases in the published literature, not in books. So that is another big problem, challenge we face when you talk about these courses. And but most importantly, you should study books and try to understand the basic part of the course so that you can use such concepts for your own research or technology developments or preparation of different kinds of new materials. So thank you for your attention. Thank you for your participations in large numbers. I know many of you have joined with a lot of expectations. I hope I have lived up with the expectations and did injustice to the course. Thank you again for the attentions.